Welcome back. So this is our 50th video about the Markov networks, and now we're going to discuss the variable elimination algorithm. So the variable elimination algorithm will be applicable to the Markov networks. So let's take one simple example and see how it works. We're going to take the voting example that we are so used to, composed by these four factors and this undirected graph here, and we're going to compute the probability of A and B. So this is going to be our first query. So this marginal query will be computed in the following way. So we have this probability of A and B. We needed to introduce the remaining variables of the Markov network, and in this case these variables are C and D. So what we do the case analysis, and we introduce those variables here. Okay, so now that we have the joint distribution over all the variables in the network, we can use the Gibbs distribution to compute that probability. And so now we're going to factorize the distribution according to the clicks that we have in the graph. So this is a pairwise Markov network. So the clicks is going to be this. So we have a factor phi 1, another factor phi 2, phi 3, and phi 4. All right, now what we can do is to eliminate for now the partition function, and so we're going to take this 1 over z out of the way, and we're going to say that this number here is going to be proportional to what we have in this third line here. So the idea is that the partition function will not change the numbers. We're going to just renormalize them to sum to 1, so we can put that aside for now, and later on we're going to see how we can normalize things in order to have the probabilities. So eliminating the partition function, and now we have just the remaining of the equation, and that looks very familiar to us. So we have those factors phi instead of the probabilities that we had before, so we just move the summations to the points where we're going to eliminate the variable. So we want to eliminate the variable d, and we have these two factors here that mention variable d, so I can move the summation to this position here, and so I'm going to sum over d for these two factors phi 3 and phi 4. For the elimination of C, I have just one factor that mentions, actually two factors that mention C, but just the phi 2 that we can move on. So we can put this thing outside the summations, and we can move the summation for C here. So it's going to be this thing. So our equation in the end is phi 1 AB times the summation over C of phi 2 BC, the summation over D, and phi 3 CD times phi 4 DA. All right, so now we're going to start doing the multiplications. So we're going to join these two factors here in a single factor, and we're going to eliminate the variable D. Let's see how it goes in the next slide. Okay, so just remember, we are eliminating variable d, and we have two factors here and here that mention variable d. These are the only factors that mention variable d, and we're going to join them. So we're going to take the joint factor will mention variables c, d, and a. So we have here the variables c, d, and a, and we take all valid assignments, and we look here to see which one's going to be the compatible assignments here. So C, D, and A, we have C, D here, 1, we have D and A here, so it's going to be 100, that's check. Another one is C, D, and not A, so we have C, D again here, and D and not A we have here, so it's going to be 1 times 1, and 1, check, and we continue doing that. So if we compute this joint factor, we'll have this factor here. All right, so let's look at the next slide. Then I'm going to remove the variable d. Okay, now just reorganizing things, what we got is we multiply these two factors together, and we got this new factor here. I'm calling this new factor the big phi 1. and I'm going to eliminate the variable d, so I'm going to do this operation here. And eliminating the variable, you should remember, it will work exactly as we had before with the Bayesian networks. Actually, those operations of join factors and eliminate the variables, they were not specific for Bayesian networks. They were defined over factors, so we are just reusing those operations. In fact, if you look at the tutorials, we're going to see that we can just reuse the code that we developed for the Bayesian networks that operate over factors for the Markov networks. So in order to eliminate the variable d, what we do? We take two compatible assignments and we sum them. So as variable d is a binary variable, we're going to take this guy here. We're going to take the same assignment that has not d, and we're going to sum together these two values here. And we're going to do that for all of them. So here we have a c and not a, and here we have a c and not a, and here we have d and not d. We're going to sum these two. And we're going to keep doing this, and we get the variable d eliminated. So let's take a look on the next slide. Great. So I'm going to call this new factor the tau1. So this is the tau1. It doesn't mention variable d anymore because variable d was eliminated, and we have it here. So I'm just using those two letters to specify the factors. One is going to be the big phi that we have the join operation, so it's going to be before summing out the variable, and we have the tau factors that are after the elimination of the variable, just to keep it consistent, and going to be a little easier to understand. So all right, so now we don't have the variable d anymore, so we can see here all the factors, and then no one mentions variable d. So we eliminated variable d, and we're going to continue to do that, and now we needed to join these two factors here. It's going to be the phi2, that is this guy here, and the tau1 that we just computed. And so these two factors are the factors that mention variable c. We can see variable c here and the variable c here. I'm going to join them, and later on, you're going to eliminate the variable c. So let's take a look at how to join these two factors in the next slide. Great. So this is the join factor. So we are joining these two factors here, the tau1 and the phi2. They mention variables a, c, and b, c. So at the end, you're going to mention the variables a, b, and c. So we have here the factor that mentions the three variables. I'm going to call this factor the big phi2. And what we have to do, we have to multiply the entries that are compatible with this assignment here. So we have CA is here, we have B and C, we have a BC here, so it's going to be 100 times 200, it's going to be 20,000. Great. So we have this assignment here where we have again C and A, and now we have it not B and C, so not B and C is here, so it's going to be 200 times 1, and be 200 here. So let's check. So after we have multiplied all those entries, we have this new factor that mentions variables C, A, and B, and we needed to eliminate the variable C, so I'm going to do a summation here over variable C. Okay, in order to sum over the variable C, let me just erase this, so yeah, going to be not so messy, and so we're going to sum over variable c in order to eliminate the variable c. So what we're going to do, we're going to take the compatible assignment that we have here, a, b, and we have again a, b here, going to be c and not c, so we are summing over all possible values of c, but c is binary. I'm going to sum these two entries here. Great. And I'm going to keep in doing this, right? So we have A and not B, A and not B for the two possible values of C. I'm going to sum these two entries here. And keep in doing that, and we're going to have a new factor. And we're going to keep that, we're going to call this the tau2, and we're going to be over A and B because we are eliminating variable C. Let's take a look on the next slide. All right, so now we have this tau2 over A and B. Here it is. Mentions variables A and B, and this is the summation, the values that we saw in the previous slide. So now we got to the situation where we have we have two factors mentioning the same variables A and B that are the query variables. So this is a situation where we got to the end of the elimination order, but instead of having just one factor, we have two. It can happen. We may have more than two factors. In fact, there are remaining. So you should remember that at the end of the variable elimination algorithm, we have a final step that we do a joint of over all the factors there are remaining, and we have a final factor. We can do that or not depending on the application. In this case, it will be interesting because we want to compute the probability of A and B, and we have still two factors. So that's going to be the last step of the variable elimination algorithm, where we join the factors that mention the query variables, and in this case, we're going to put these two factors together. Take a look that we are not do the summation. We are going to do the multiplication in this case because we don't have any more variables to eliminate. So it's going to be just one joint of the factors, and the algorithm ends. So again, so we have these two factors, both mentioned variables A and B. So I'm going to multiply them together. We know how to do that. In this case, it's going to be very simple because we have just to multiply the compatible rows here. So it's going to be the first row times the first row in one table times the first row in the other table, the second row here times the second row here, and we finish with that. So take a look the next slide, what's going to be the final result, and so here it is the final factor. Its final factor has these large numbers, and let's see what happens when we normalize this factor. And yeah, we get the marginal probability over A and B. Exactly the same number that we haven't seen before in the previous slide when we mentioned this. So what we see is that differently from the Bayesian network, when everything is naturally normalized, in the case of the Markov networks, we needed to have one final step where we go from the unnormalized distribution to the probability distribution that is normalized. So there is one final step. So everything that's going on here is basically we are summing all over those numbers here. We have the partition function z, that's going to be a constant here, and we're going to divide every entry here by z. So it's just a normalization, and we got these numbers here. So that's good. So in some sense, that's good news because we don't need to compute the partition function in another step, right? And that's going to be very expensive if we had to compute all the entries in the joint distribution and sum over all those entries. What's going on here is, in fact, that because we do the multiplication and the summation of the numbers, we are not losing anything. So the numbers accumulate, and we will have the partition function in the numbers that we carry in these factors. So at the end, if we sum those numbers, we get the same number that we would have if we were summing the entries in the full joint distribution. So that's great news. So the variable elimination algorithm works for the Markov networks. And let's take a look at now in another example. Okay, let's take a look in one second example, and now we're going to compute a query that has evidence. So in this case here, we're going to compute the probability of B given C equal true. So we start by setting the evidence. So what I mean is that we go here at the node C, and we set the evidence, and the evidence is C equal true. So what we have to do is to eliminate the rows in the factors that mention C that do not match the evidence. So I'm going to eliminate this row and this row. I'm going to eliminate this row and this row. All right, so let's take a look at how the factors are now. So these are basically the same steps that we did before. So we started with the probability of B and C, and we'll try to normalize it later exactly how we did with the Bayesian networks in order to get the probability of B given C. So we started with the probability of B and C that allow us to introduce the remaining variables that are A and D, and we do that by case analysis. I'm going to use the little c here in order to make it clear that C is not a variable, but they're going to be now a value. So now we have C equal true. And we can use the Gibbs distribution in order to get the factorization for the Markov network. And it's going to be this step here. And we need now to move the summations to appropriate locations here. So we say first that this term here is equal to this one. Actually, it's not equal, it's proportional to this one because we are removing the partition function. So now we are in position to move the summations. We're going to sum over the variable d, so we're going to put the summation over d here because only phi 3 and phi 4 mentions variable d. And we have the summation over a. Now we're going to eliminate the variable a, and we have these two terms, so we're going to change them. So we're going to put the phi 2 before the phi 1, and they're going to move the summation of over a to the position next to the phi 1. So we have like exactly what we have here. So we're going to be the phi 2 that mentions variables b and c times a summation over a for phi 1 ab times a summation over d for the factors phi 3 cd and phi 4 da. So the first two factors they're going to join are the phi 3 and phi 4. So we can look for them. Phi 3 is here, phi 4 is here. So I'm going to multiply them. We're going to create a new factor that mentions little c, d, and a. And we're going to look at the compatible assignments and multiply them. I'm going to do that in the next slide. So great. So we have this new factor here. I call in the new factor big phi 1. And so we just, everything that we have to do is look at the assignments and look for the compatible ones. So this mentions CD, so it's going to be 1. And this on top here mentions D and A. So it's going to be 1 times 100. We have it on 100. And we keep in doing that. Exactly like we did before. So after we do this, we need to eliminate the variable, and in this case, we're going to eliminate the variable d. So here is variable d. We have to eliminate that, so we're going to sum this assignment with this assignment and this assignment with this assignment. Let's take a look on the next slide. Okay, so now we have this this new factor here. We need to eliminate the variable d, as I mentioned in the previous one. So I'm going to sum these and these and these and this. So we have, you should have 210,001. And let's see if we have that. In the next slide, you're going to have a new factor that we call the tau 1. So let me just write it here. It's going to be the tau 1. All right, now we have the tau 1. So the tau 1 is defined over little c and a, and it's here. It is a factor that mentions a. And now we're going to eliminate the variable a, so we need to multiply by all factors that also mention a. There is just one factor that mentions a, that is this factor here. It is the phi 1. So we're going to multiply these two things together. And we're going to multiply this one and get the new factor. And we're going to call the big phi 2. So to multiply this, we only have to look for the compatible assignments as we have done before. So we have it here. So this new factor will mention little c, a, and b. So we have one assignment here again. This assignment is compatible with this one and also compatible with this one. So we're going to multiply 200 by 30 and we have a 6,000. Okay, so now it's time to eliminate the variable a. So here is a variable a. So I'm going to eliminate that by summing the compatible assignment over all possible values of a. So it's going to be the sum of these two rows here. All right, so we have not eliminated a yet. I'm going to do now. So again, a is here, sum this and sum this, and we should have one factor that mentions little c and b. So here it is. Again, we end up with two factors One is the phi 2 over B and C, and the other one is the tau 2 over C and B. So we can multiply those factors together. So we're going to just multiply these guys and these guys, and we will have just one factor. Again, this factor will be unnormalized. So here it is unnormalized, and we needed to normalize it in order to compute the answer to our query, that is the probability of B given little c. So here it is. So we just sum up these two values and we divided each one by z, and we got the answer to our query. So this is what we got after the elimination, after the normalization, and these are the probabilities that we were looking for. Good. So let's take a look on one last example, and now we have the potentials expressed in the form of the energy function. So it's going to be slightly different than what we had before. So let's suppose that we want to compute this marginal here, so the probability of A and B, and in order to do that, we factorize the joint distribution according to the Gibbs distribution expressed in terms of energy functions. But we need first to, in order to get this joint distribution here, we need to introduce the variable C and D. And in order to introduce the variable C and D, we do case analysis and we sum over all possible values of C and sum over all possible values of D, and we get the joint distribution. Now that we get the joint distribution, we can apply the Gibbs distribution, and in this case, it's going to be slightly different. So we have this thing here, gonna sum over C and D, and now we have the partition function, and we have this exponential defined over the potentials, and the potentials are these psi 1, psi 2, psi 3, and psi 4, and basically they are defined here. So we saw that those psi potentials, we can compute them from the factors that we had before, just applying the operation, the minus log of the value of the factor that we had. So we have this summation for all those potentials now. All right, so we wanted to get rid of the partition function, so we just remove it and we say that it's going to be proportional, and we have this situation. And now we want to move the summation. So we want to move the summations over the variable D to this position here where we can eliminate D, and these are the factors that mention D. And we want to move the summation over C to this position here so we can eliminate the variable C. But the problem is that we have this exponential function, and if we do the summation inside here of the exponential function, what is going to happen is that it's going to modify our final results, because the exponential function is not a linear function. So if we do the summation before computing the exponential, it will not be the same thing as applying the exponential first and the summation later. So we need to be very careful. But everything that we need to do is to transform this exponential of sums into a multiplication of exponential functions defined over each of the potentials. So that's very simple to do. So we keep here the summations, and now we're going to have a multiplication of the first term here is exponential over the psi 1 times another exponential over the psi 2 and another exponential here. So we have this multiplication of exponentials. Great. Now that we have this, we have something that's very similar to what we had before, and we are ready to move the summations in order to eliminate the variable. So we move the summation over D to this position, and we move the summation over C to this position, and we continue the algorithm exactly as we had before. Just one small detail here is that when we have a situation like this, where we have this multiplication here over two factors that mentions variable D before we eliminate the variable D, and in this case we could have what we had before. So in this case here we could have the exponential minus whatever we had before here. So we had psi3 CD plus the psi4 DA, and we computed these first, and after we have computed these, we eliminated the variable D as we had before. Because we have this multiplication here, we are not eliminating any variable, so we are not doing any summations with this term here, so we can compute as we had before and eliminated the variable D afterwards. Alright, so I guess that is enough for this video. So let's take a break now, and we're going to continue in the next one where we're going to discuss the conditional random fields. So see you soon.